In this video, I'd like to discuss a little bit more about related rates, and we'll do so in the context of a few of our Math Excel problems. Here's number 12 from this first week's assignment on Math Excel, and this one gets a bit interesting because the volume that's needed to in order to calculate the amount of water that's in this pool is really a compound equation. It's not quite as simple as some of the examples we've seen so far. But essentially, we have this swimming pool that's 50 meters long, 20 meters wide, and it's at least 1 meter deep, but it tapers down to a depth of 3 meters, at least in my example. And so, for this particular problem, and in problems like it in general, it might be easier to consider a more exaggerated diagram so that we can see exactly what's going on. So on one end of the pool, it's at least 1 meter deep, and then it tapers down to a distance of 3 meters. And we have a side view profile that's essentially a trapezoid here. And it's worth noting that this upper component of the swimming pool is rectangular, while this lower component is triangular. And that's particularly interesting to consider when we start transforming this into some sort of three-dimensional object. So if I start adding the sides to this pool, we sort of see something kind of interesting. This lower portion of the pool ends up being just a triangular prism. And if we're imagining, water that's being poured into this pool from some supply, it starts to fill from the bottom of this triangle upward. And as the water level rises, for a significant portion of the time, we're just filling up this triangular prism of a pool, this triangular prism. And the volume, of course, is going to need calculus to compute because the dimension of this shape is changing as this water level rises. As we start rising here, the shape of this end panel is slightly different. So therefore, when we're talking about the total volume of this pool, rather than thinking about this as some sort of trapezoid, trapezoidal prism, let's consider this a triangular prism plus this rectangular prism. And the total volume of this pool, therefore, would be equal to 1/2 of the base times height times width. Now that's going to take care of this triangular side of the pool. There's our base. My software kind of froze on me there. Let me try that again. So we've got this triangular face that has a base and a height to the triangle. If I multiply that area of that triangle times the width of this pool, that's going to give us the volume of the water associated with this triangular wedge portion. So again, if we're talking about the total volume of the pool, that's half of base times height times width. And then to that, we will add the volume of this upper component. And again, with this upper component being a rectangular prism, its area would be length times width times height. Now in my example, we had these dimensions known, that on the shallow end, the pool was 1 meter deep, and on the deep end, it's 3 meters. So there was 2 meters associated with this wedge and 1 meter associated with this prism. The pool was 50 meters long and 20 meters wide. So when we account for the rectangular prism component of this swimming pool, we have a length of 50, width of 20, and a height of 1. But on the triangular component, this is what's going to be changing. The dimensions of this base and the height are constantly changing, because when the water level is really low, the base and the height is going to be different than the values when the water level is a little bit higher, the base and the height there. Now, the width of the pool is always going to be a constant 20 units wide, so that's good to know. Um, but the base and the height values, well, that's just a little bit different. And with that being said, the dimensions of any one of these triangles, as time progresses, any one of these triangles that are formed up until this point, they're all similar in shape to one another. And so all of their side lengths are proportional. And so if I talk about base here and height here, I may end up calling those base 1. Well, actually, let me relabel that. Let's call this base 1 and height 1. As I talk about those two dimensions, they are going to be similar in size or proportionate in size to the base of 50 and the height of 2. And so we've got base 1 divided by height 1 is equal to 50 divided by 2. No matter what values the base and the height take on, that fraction will be equivalent to the fraction 50 over 2. And with that in mind, it would be nice to rewrite this function in terms of just a single variable. The variables length and width and height have all disappeared on account of the rectangular prism. This width measurement is now gone, and so now it'd be nice to write this function either in terms of b or h. And as we look at our instructions here, the instructions do say to let v, h, and w be the measurements that we need, and we would like to write an equation relating v and h with one another. So since our goal is to rewrite the volume in terms of the height of the water, we might end up solving for h1 here. So we know that 50 times h1, this cross product, is equivalent to 2 times b1, and therefore b1 by itself is equal to 50h1 divided by 2. And I do it that way. I solve for b so that I can replace the letter b with some sort of formula involving h. Now I used B1 and H1 here to differentiate between the base and the height of the original rectangle, but as we substitute this component into the equation up here, we don't really need that subscript of H1 anymore. So I'm going to replace the base of the triangle to be 50 over 2h. H, of course, will retain as h times 20 plus 50 times 20 times 1. And we can clean this up a little bit. Half times 50 over 2 will, of course, be 50 over 4. 20 divided by 4 is 5. So we've got 50 times 5, which is 250. H times h, which is h squared, plus 1,000. So the total volume of this swimming pool is going to be 250h squared plus 1,000. And really, this formula does have a domain restriction. We haven't spent much time talking about that, but the domain restriction in this case, since h is a height measurement from 0 to 2 in this case, we're really only saying that this equation would be good for any h value that's on the domain from 0 to 2. And I think that's worth noting because we want to know what the volume formula would be at precisely 640 minutes after filling the pool. And we are filling at a rate of 1 cubic meter per minute. So we would essentially like to know what component of the volume formula we're using when the volume is 640 cubic meters. If we had, say, 2 cubic meters per minute, then we'd be talking about 1,280 cubic meters of water that had been put into the pool. But that's not the case here. We're talking about 640 cubic meters. And when h is 2, for example, when the height of the triangular section is 2 meters, well, of course, 2 squared is 4. 4 times 250 is 1,000. So if we really think about it, the volume formula that would be appropriate is simply 250 h squared. We won't even worry about this 1000 component until until 600, I'm sorry, until 1000 minutes have passed. So for the first 1000 minutes, this is the only formula that's necessary for us to consider. And then finally, after 1000 minutes, that's when this lower portion of the pool is going to be filled. And then from there, we've got another 1000 gallons or another 1000 minutes to fill the rest of the pool. And the only reason why I need to make this change here, it doesn't affect our calculus all that much, but for Math Excel, when they're asking for the formula, when they're asking for the formula or an equation relating V and H at precisely this moment, well, the formula volume is going to be equal to 250 times H squared at that moment. It's not until after the 1000th minute, which is way after the 640th. It's not until the 1000th minute that we have to consider what's happening with the rectangular component above. Additionally, that makes our next step a little bit easier because if we have to differentiate this formula with respect to time, then that becomes a bit easier to do. So if we apply our derivative with respect to time on both sides of the equation, what we end up with is dv dt is equal to 500 h times dh dt. This follows our implicit differentiation from last unit. 2 times 250 was 500. The derivative would be 500h if we were deriving with respect to h, but since it's with respect to t, we have to tag on this differential. Same thing with the derivative of v over here. The derivative of v is technically 1, but since we don't have a matching unit here or a matching variable, we have to tack on this dv dt. So I think that expression would be good to answer the second question, where we have 500 h times dh dt. And then therefore we can answer the question, how fast is the water level rising 640 minutes after the filling of the pool begins? So how fast, what is the rate of change? This is going to be dH dt when 640 minutes has passed. Well, we were told that we're filling this pool with water at 1 cubic meter per minute, and so that's a measurement of volume with respect to time. So we have dV dt. We can determine the height, of course, with a little bit of algebra. And with height and dV dt known, we can then solve for dH dt. So as we relate this formula here, just going to do this off to the side, we knew that the volume of the water would be equal to 250 h squared. And after 640 minutes, we have 640 cubic meters of water that's been put into the pool. And of course, if your problem varied, let's say on your example, you had water being poured in at 2 cubic meters per minute, then you would have put 1280 here or something like that. So if 640 cubic meters is equal to 250 times h squared, then 640 divided by 250, and the square root of that expression would then equal h. And as it turns out, that math there is pretty nice. 640 and 250 will reduce to 64 over 25, and the square root of 64 divided by the square root of 25 is what's being accomplished by taking the square root of the entire fraction, and now we're dealing with a height of 8/5. These numbers ended up working out very nicely for us. So the rate at which the pool is being filled with water was 1 meter cubed per minute, and we had 500 times h, which was 8/5 meters, times dh dt, which would be meters per minute. The change in height with respect to time is meters per minute. And we ended up having a measurement of meters inside of this coefficient of 250, whether we recognized it or not. Height squared would be meters, would produce a unit of meters squared, and 250 itself contained a unit of meters as well. So it was implied, not explicitly stated, that the 500 also contained a value of meters. And so as we divide by 500 meters and divide by 8/5 meters, we will end up with a unit of meters per minute. So 1 divided by 500 and divided by 8/5 will produce a unit of meters per minute, which is perfect because dH/dt also requires a unit of meters per minute. And you can try to do this with mental math or use a calculator. I ended up using a calculator off screen and got 1 divided by 800 meters per minute. So the rate at which the water level is rising 640 minutes after the pool started being filled is 1/800th of a meter per minute, which is very, very, very slow. This pool must be extremely large because if you've ever watched a pool being filled, you would understand that a cubic meter of water being filled every minute is quite a lot of water. So if the water level is rising 1/800th of a meter, this pool must be very large in order for it to be raising the water level to be rising that slowly. Now this final question, well, keep in mind the total volume of the pool is equal to, we had that upper rectangular prism that was 1,000 cubic meters, and then that lower triangular prism that also computed out to be 1,000 cubic meters. And so we've got a total of 2,000 cubic meters that are necessary in order to fill the pool. And if we're filling those at 1 meter per minute, then the time is going to have to be 2,000 minutes. And so this question really is unrelated to the calculus. This is really asking, based on the total volume of the pool to its highest point, how long will it take to reach that? And that's essentially the volume, the total volume of the pool divided by the rate at which it takes to fill that pool. So lots of interesting components here, and there was some interesting geometry that goes with it. But ultimately, once we get past the hangups with the geometry, then I think the calculus is pretty straightforward. We can apply the implicit differentiation and then make sense of the math that goes with that. Now, the next problem I wanted to discuss was number 14, and this one I don't think is going to be quite so challenging, but it's an interesting problem nonetheless. We have this ladder that's leaning up against a wall, and it's 13 feet long, and what's happening is this ladder is falling, it's sliding away from the wall, so its horizontal distance is increasing while its vertical distance is decreasing. So if we think of x and y and z being the three values in this particular problem, z remains constant at 13 feet. The ladder itself is not changing in size. And so, in a sense, we can think of dz dt, the rate at which the ladder length itself changes over time, is 0 feet per second. The ladder itself is not changing in length. But as the ladder falls down the wall, then its vertical position is changing with time, and so is its horizontal position. Jack begins pulling the foot of the ladder away from the wall at a rate of 0.6 feet per second. So this measurement down here, dx dt, is equal to 0.6 feet per second. And it's a positive number because this horizontal distance is increasing. We would like to know how fast the top of the ladder is sliding down the wall. That's our dy dt, and we should compute a negative result for that because the height above the ground is decreasing. And we would do this based on the foot of the ladder being 12 foot away from the wall, 12 feet away from the wall. So at precisely the moment when x is equal to 12, can we determine dy dt? Well, a quick computation would help us find out what y is equal to. And we know that x squared plus y squared has to equal z squared. So 12 squared plus y squared is equal to 13 squared. That means that y squared is equal to 169, which was 13 squared, minus 144, which was 12 squared. And so y squared is equal to 25. So y itself must be 5 feet. Okay, so we've got lots of information here. Let's see if we can relate them to one another using a bit of calculus. The relationship between the side lengths, of course, was x squared plus y squared equals z squared. That's the outside formula. That's the outside piece of information we need to know to make this problem work. And if we differentiate this formula with respect to time, if we differentiate all of these components, that is, with respect to time, then we should be able to answer this problem. We should be able to find out dy dt, which is a question that's being posed right here. So the derivative of x squared would be 2x, but since the variables disagree, we're going to call this 2x times dx dt. And similarly, we have 2y times dy dt. And then lastly, we've got 2z times dz dt. Now, the x value in this problem, of course, was given to us, and that's 12. And the dx dt is 0.6. The y component we had to calculate, but ended up being 5 feet. What we don't know is the dy dt value. In fact, that's exactly what we're solving for. And then lastly, our z value, the length of the ladder is 13, but dz dt, the rate at which the ladder length is changing, is 0. And so we've got 0 on the right-hand side of the equation, because 2 times 13 times 0 will be 0. And we have 2 times 12 times 0.6 plus 2 times 5 times dy dt on the left. If I move this component to the right side of the equation and then divide by 2 times 5 or divide by 10, then I'm going to be able to isolate dy dt as 2 times 12 times 0.6 divided by 2 times 5. And I should have indicated that this was a negative number because I subtracted it from the left to the right-hand side. And as I enter that in the calculator and calculate a result, I ended up with negative 1.44. We consider the units that are being used. We've got negative 1.4 feet per second. And that answer makes some sense to me because the top edge of this ladder is decreasing in height. So there the negative 1.4 feet per second is appropriate. Now, I did all of that work without paying close attention to the questions as they're posed in Math Excel, and I would argue that you'd be able to do the same. We're faced with a problem here. We should be able to solve it, and you can do all of that work on your sheet of notebook paper and then decide what components would be necessary to fill in the questions for Math Excel. So I'm going to leave that up to you to make those substitutions or to be able to answer the question on Math Excel from the work that you've done to answer the problem. I'm going to skip ahead past 8 and instead talk about number 9. We have a piston that's seated at the top of a cylindrical chamber, so we're inside of this cylinder, and the radius of the piston is 5 centimeters. When it starts moving, into the chamber at a constant speed of 3 centimeters per second, what is the rate of change of volume? So rate of change of volume is going to be dV dt, while this movement here in the chamber is the change in height with respect to time. When the position is 10 centimeters, when the piston is 10 centimeters or has a height of 10 centimeters from the base of the chamber. So it appears to me like the formula that we need is some sort of volume of a cylinder. And if you recall, the volume of a cylinder is the area of the base, which is pi r squared in this case, times the height of the object. And what's particularly interesting is that the radius is not going to change. The radius is stuck at 5, while the height of this cylinder changes as the piston drops in. The height measurement will change over time. So the height of the cylinder is going to change as time passes, but the volume is always going to be, at least the area of the base is consistent. So we've got 25 pi times h to represent this volume. But again, the radius remains fixed. So if I were answering this question on paper, I wouldn't even consider r. However, for Math Excel, it does look like that they're going to ask that of you. So the volume formula you can use, of course, is this guy. And when you differentiate it in terms of t for time, well, it looks like there's going to be a bit of a chain rule. I'm sorry, not a chain rule, but a product rule involved, which shouldn't be too challenging, I wouldn't think. But it's good to be aware of that that's what you're going to face as simplifying this. You can always, of course, compute the derivative of this particular formula and compare it to the original after you substitute a known radius of 5. So I'm not going to walk entirely through that. I do want to challenge you and let you think about that on your own. Also use the Math Excel help tools to see if that will clarify any questions that you have. And of course, you can bring more of your questions to me as needed. But I thought I'd share this one with you just because there really are a couple different ways to consider this when approaching this particular question or a problem like it in the real world. Hope this video helps, and sorry to leave you hanging like that at the very end, but I know you can manage. Thanks for watching.